All right, let's get right into it. When you picture an explosion, what's the first thing that comes to mind? Probably size, right? You figure more stuff to blow up means a bigger boom. But what if I told you the shape of an explosive could be just as important, maybe even more so? We're about to look at some really mind-blowing research that totally reshapes our whole understanding of explosive power. And that's really the big question here, isn't it? We're just wired to think that mass is king. But, science absolutely loves to poke holes in our gut feelings. And this is one of those times. We're going to see how a hidden variable can completely change the entire game. So you've got two things at play here. On one side, you have the charge mass. That's the obvious stuff, how much explosive material you're working with. But on the other side, you've got the charge geometry, the hidden variable. This is all about the specific shape of that material. And the real secret, the key to all of this, is how these two things work together to define the true force of a blast. Now, to really wrap our heads around this, we need to be clear on what we're even measuring when we talk about the strength of an explosion. It's not just about that giant fireball we see. No, the real story is in the invisible, powerful wave of force that just erupts outward from the center. And the key term we need to know is shockwave over pressure. Now, I know it sounds super technical, but trust me, the idea is actually pretty simple. It's just a measurement of how much the pressure skyrockets above normal, everyday air pressure the very instant that shockwave hits you. That is the force that does all the real damage. Let me break it down with an analogy. Imagine you're pushing against a wall, nice and slow. That's a gradual change in pressure, right? But what about a sudden punch? That's a huge amount of force delivered in a split second. That intense, sharp impact, that's overpressure. See, it's not just about how much force there is, it's about how ridiculously fast it shows up. So if you've got this mild idea that shape can affect overpressure, how in the world do you test it? Well, some researchers set up this really cool experiment, basically pitting different explosive shapes against each other in a kind of scientific showdown. And here are our contenders. The researchers used explosive charges that all had the exact same mass, but they had different shapes. First up, your standard cylinder. That was the baseline, the control group. Then things get a little weird with a triangular prism, and for the grand finale, a really complex 5-point star prism. So the big question was, would they all deliver the same kind of punch? Okay, so trying to measure something that's over in microseconds is, incredibly tricky. What they did was use these amazing high-speed cameras to record everything. This let them pinpoint the exact moment that invisible blast wave hit their sensors. It's just a really clever way to freeze a moment that's over in a flash. So they have all this timing data. What's next? Well, they plugged it into a special set of equations called the Rankine-Haugenot relationship. The easiest way to think about this is like a shockwave calculator. It's this fundamental tool in physics that takes timing data and spits out the numbers for things like pressure and density. It's the magic step that translates a stopwatch reading into a hard number for that punch we've been talking about. And here we go. This is the moment of truth. The experiment is done, the data's been crunched, and the results? Well, they weren't just interesting. They were a genuine shock, completely flipping the script on the conventional wisdom about what makes an explosion powerful. The bottom line is stated right there in the research findings. Shape really, really matters. Those non-spherical shapes, the triangle and especially the star, produced way different and often much, much higher overpressures from the good old cylinder, even though, and this is the key, they all have the exact same amount of explosive fuel. And just look at this graph. I mean, the bar chart makes it crystal clear. The cylinder, that's our baseline. The triangle? Yep, it produced a noticeably higher peak overpressure. But the 5-point star? Whoa, it was in a completely different league, generating the highest overpressure by far. The takeaway here is just stunning. Same amount of fuel, but the star-shaped charge delivered a much, much sharper punch. Now believe me, this is way more than just a cool science experiment for a lab. Understanding that you can use simple geometry to direct and intensify energy, that has some massive real-world consequences, everywhere from heavy industry to national defense. So why should you care? Well, think about it. This could lead to way more precise and efficient explosives for things like demolition or mining, focusing all that blast energy exactly where you need it and nowhere else. And on the flip side, it helps us design better armor and stronger buildings, things that can actually stand up to these complex shaped shockwaves. Really, at its heart, it just gives us a much, much deeper playbook for understanding how energy works. And all of this leaves us with one last big idea to chew on. This research proves that just by changing a single, simple variable, in this case shape, we can completely change an outcome we thought we had all figured out. It really makes you wonder, doesn't it? What other basic rules of the world have these hidden variables we just haven't even thought to look for yet? What other facts are just waiting to be reshaped?